So I'm also going to take a few minutes or maybe 10 minutes to talk about this, what is happening, right. So I mean, we did all this probabilistic analysis and so on, but I want to talk about the linear algebraic aspect of this, right. So I mean, it's always good, right. So when a fundamental lemma like this is put out, it's always good to understand it in multiple points of view, so that we kind of gain a more rounded perspective of what's going on. So let's try to understand this lemma slightly differently, I would say, right. So for that, let's look at it from a linear algebraic lens. Of course, we cannot get rid of the probabilistic lens, because fundamentally it's a random transformation. So the probability is still going to be there, but then we have not really seen this as like a transformation. We have seen this somehow as an estimation, right. So though I'm calling it as 1 by square root k r, right. So always I have not really looked at the transformation m equals 1 by square root k r. I have not looked at the properties of this matrix. We are always looking at properties of individual elements, or we started by motivating it as like an estimation problem, right. So each of these components of V can be thought of as Gaussian random variables with mean 0, variance, length squared. So the length is hiding somewhere in the variance, so let me estimate the variance, and then what is the corresponding transformation, if I am trying to estimate the variance. That was our attack earlier. So now let's do a purely linear algebraic point of view of trying to understand this. Again, so the idea here is just to throw some insights into this very interesting transformation from a linear algebra point of view. Let's see where that takes us. So linear algebraic point of view of JL. Okay, so let's say I have this matrix M, which is 1 by square root k r, right. So this is my matrix. Now the linear algebraic view is to understand this matrix as an operator, right. So any matrix, linear algebra would tell me, and the fundamental idea in linear algebra is to understand any matrix as an operation, and then break down this into more fundamental operations using the singular value decomposition, and I'm sure all of us are aware of what this is. So this is just any matrix M, rectangular, square, doesn't matter. So for our purposes, we are going to think of this as a K cross D matrix, because that's what our matrix is. Can be written as U sigma V transpose, where U is a K cross K orthonormal matrix, sigma is a K cross D, like a pseudo diagonal matrix. So I'm calling diagonal within quotes because it's not square, so diagonal matrices typically are associated with square matrices, but we understand what I'll tell you what sigma is if you have not seen before. V transpose is a D cross D orthonormal matrix. Okay. D cross D orthonormal matrix, right. So sigma itself is, so basically before talking about sigma, so if I have like a vector u and then I multiply mu, what happens is U sigma V transpose U happens. So sigma itself is, when I say K cross D, K is, I'm going to think of K as small, D is large. So K cross D is going to be like this, 1 to K, 1 to D. So you are going to have these what are called as singular values, sigma 1 squared, or let me just call it sigma 1, sigma 2, sigma k, and then everything else is 0, right. So, there is this k cross k guy sitting inside, which is the actual diagonal matrix, and then everything else is just 0, right. So, that's how sigma is, the matrix sigma is, and these are the singular values, which also happen to be square of these are positive, these are square of the eigenvalues of M transpose or M transpose M, both have the same eigenvalues. That is the singular value decomposition for you. So, geometrically, what this is kind of telling us is the following. This is also something that some of you may be aware if you have seen SVD before. So, let us say in 2D, I can consider vectors of length 1. Well, I mean, it's as an operator, the matrix M operates on any vector, but let us say I consider only vectors of length 1, because let us say if I have a vector which is not of length 1, then I can treat that as some scaled version, right. So, let us say this was my u, and then this is let us say 0.3 times u, which has length 1. Well, if I apply M to u, I can study M's application on 0.3 times u, and then I can divide it by 1 by 0.3, right. So, this is basically 0.3 times mu by 0.3, which is mu. So, basically, because it is a linear operation, does not matter how much scaling that I have in the original space. This I am going to, so if M maps u to v, then M maps 2 times u to 2 times v, right. So, that is the linearity property. So, it suffices to study the operation, what an operator does if I only study unit vectors, and it is typically easy to understand the unit vectors because the rest I can kind of understand. Okay, so, if I take a unit vector u here, so let us say this is in RT. Now, M itself is u sigma v transpose, and then the first thing that happens is I am doing v transpose u. I can treat this as 3 steps. The first step is I am doing v transpose u, which means that, remember, v is in n cross n, d cross d, u is in d cross 1. So, what I am getting is a d cross 1 vector, and v is an orthonormal matrix. Basically, it is a rotation matrix, right. So, you can think of it as a change of basis in the d dimensional space. So, geometrically you can visualize it as some kind of a rotation matrix. So, what is happening is this u gets first rotated, right. So, the u was here, and then it gets rotated and it goes to, let us say, somewhere here in the original space itself, because v transpose u is still in the original space, right. Now, after that, what I do is I kind of do scaling. Now this is after I apply v transpose. Now, then the next step to apply is sigma, because matrix application happens from right to left. I apply sigma. The moment I apply sigma, what is essentially happening is, if v transpose u had, think of it as like this. So, if v transpose u had a1, a2 till ad, these were the dimensions, and then I have a k cross d diagonal matrix. So, this is sigma 1 followed by 0, 0, sigma 2, sigma k, and then everything else is 0. So, this is k cross d, this is d cross 1. So, if I do the multiplication, what I am basically getting is sigma 1 a1, sigma 2 a2, and so on, right. So, basically this is sigma 1 a1, sigma 2 a2, sigma k ak, and then the remaining are all zeros, right. I mean, basically this is all I am getting, right. So, I am kind of scaling the first k coordinates of this d cross 1 vector using sigmas. So, that is my sigmas, and that is what sigma is essentially doing. So, what this is basically sigma, you can think of it as sigma v transpose u, right. So, now this is suddenly now this is still, this is R d, this is also R d, and now I am somewhere in, I might, so it might stretch some directions, it might not stretch other directions. So I end up in maybe somewhere like this, right. So it probably stretched one direction, it didn't stretch the other direction. So I ended up here in R k. So this is in R k. So this is after I apply sigma, and then the final step is I apply u, which is again an orthonormal basis for k, which means that I am now again doing some kind of a rotation in the k dimensional space now, right. So if I do the rotation in k dimensional space, so I might end up getting something like this, right. So I don't know, so maybe it goes somewhere here. After I do the rotation, the rotations, remember, do not touch the length, right. So the lengths are still preserved after rotation. So this length and this length are supposed to be the same. So basically, so this is again in R k. So now what has happened is, three operations have happened. So you started with some u, and then we did a v transpose u, which means we rotated in the original and d dimensional space. We scaled some axis, zeroed the rest of the components, and then we so I mean the rest of the components don't matter, and then we scaled the top the k dimensions, and then again rotated it, right. So to get using u transpose, I mean basically u, which is like the basis is u transpose, and that is where I will end up with, right. So basically the mapping goes from d to k. So now if I generally think of this as the way to think of this is, if I now do this for every unit vector, now if I have the entire unit vector, this is R d, it might go to, all the unit vectors might get mapped to here, right. So maybe the one example that we saw was this guy got mapped to here. Yeah, so this was u, this was mu, this is in R k. Now if I do this for each of the points and then I track where they end up in, they will kind of end up in, like an ellipse of sorts, right. So usually, so the directions of the ellipse depends on the singular vectors and so on, right. So in this case, the one singular vector is in this direction, the other singular vector is in this direction, and then the singular value for the vector in this direction is larger. So more scaling happens in the 45 degree, and lesser, I mean shrinking happens in the the perpendicular to that 45 degree, like a 135 degree in this direction, right. So one direction has scaling, like it scales by a positive quantity. One minus 1 or minus 1 direction has a shrinking, right. So if I just look at this picture, in this case it looks like 2 dimension gets mapped to 2 dimension, d and k are the same, but then that's the idea, right. So I mean at least you can say that the singular vectors would be in these 2 directions, the singular values would be perhaps more, I mean let us say twice in the first direction, one direction, and maybe half in the second direction, because it is shrunk by half, the circle is shrunk by half in this direction, right. So that is the general principle of SVD. Now we want to see what is happening for our specific problem that we have at hand, right. So where we are looking at this randomized matrix, right. So this is how we would analyze in a linear algebraic sense. So I have this m, which is 1 by square root k r, and somehow magically the distances seem to be preserved, right. So if after I apply m to any vector, any pairs, I mean x minus y. In general, if I apply it to some u, then the distances are preserved. I mean norm v squared seem to be similar to norm u squared. So why is that happening? So if I think of m itself as again u sigma v transpose, now the intuition here is that I am not going to prove anything here, I am just going to throw some intuition here. The intuition here is that the role of v transpose, right. So v transpose takes a u in Rn, and then it maps to v transpose u. Again this is also in Rn. The intuition here is that u can be any specific vector, but when I do V transpose U, you should think of V as a random orthonormal transformation, right. So, or rather, in other words, I can call this as like a random rotation. In other words, I am just to give an analogy, I am picking some angle with which I need to rotate at random, and then I am rotating U with that angle, right. So, that is what this is. So, which means that after I do V transpose U, that vector could be anywhere, all directions are equally likely, right. So, in some sense we are, U might have a bad direction, right. So, whatever it might lead to a bad event perhaps, right. So, but then because I am randomly rotating U, now there is no bias in V transpose U. When I say bias, I mean it is not preferring any one direction more than the other, because no matter what fixed U I have, if I am randomly pushing it in one direction, it will end up uniformly in the entire unit sphere, right. So, for now I am going to assume that length of U is 1, right. So, let us say length of U is 1, like how we assumed here when we started with the unit of U in the unit vector, right. So, now this is a purely a random rotation that is happening. So, now what happens when you do like a random rotation is, right. So, now this vector, which is, let us call this vector a1 a2 till an, right. It is not preferring any single direction, that is what it means, right. So, U could be anything, U could be 1 0 0 0 0 0 0, that also has length 1, right. So, in the n dimensional space, it could be a basis vector, it could be any vector of length 1, does not matter. But then after you do this random rotation, the chance that it has 1 0 0 0 0 values is very small, right. So, or the chance that some of the coordinates have 0 values where the other coordinates have very high values is very small. Roughly speaking, what it roughly will look like the following, right. So, this guy is going to roughly look like 1 by square root n, 1 by square root n, 1 by square root n. Why 1 by square root n? Then the length of U squared is just 1 by n plus 1 by n plus n times, which is 1. Right. So, that is how it is going to look like, right. So, all the components are going to be nearly same. Of course, it will not be exactly 1 by square root n, but then it is going to be close to 1 by square root n, right. So, that is what I mean, right. So, that is why I am saying approximately. So, what we are doing is like an approximate understanding of what is happening, right. So, all these values are going to be something like 1 by square root n. So, which means that no direction is more important than any other direction, right. So, that is a property. So, where does this property come from? This comes from the fact that my M was 1 by square root k Gaussian. It's because it's a Gaussian matrix. Now you can analyze how the singular vectors V transpose of a Gaussian look like, and then I can argue that V transpose U is almost uniform. I mean, the entries are almost the same, right? So roughly 1 by square root n. That's the first thing that happens. The next thing is by sigma, right? So sigma is just going to make it, so when I do sigma V transpose U, then that's just going to be sum over I equals 1 to k sigma I ai. That's what it's going to look like, right? So it's going to take the top first k components, and then it's going to make that scale it by sigma. Now again, so this comes from very deep results in random matrix theory, that the singular values of such Gaussian matrices, I will make this a little bit more precise later on, but this guy is going to look something like square root of n by k. All the singular values look something like square root of n by k. In fact, I mean there is a matrix theory result that says that this will all be in the interval square root of n by k minus 1 to square root of n by k plus 1, right. That is a result that we do not really have to worry about here, but for our understanding we can think of it as something like square root of n by k, right. So the singular values, in other words, if it is a random matrix, if you analyze the singular values of a random matrix of the form 1 by square root k r, then those values are going to be close to square root of n by k. That is a result from random matrix theory, right. So, which means that approximately these guys are all square root of n by k, and approximately a is all something like 1 by square root n, right. So, which means the sum over this, so if I mean I should not, there is no sum happening here, right. So, basically so after I apply this, so this is going to be sigma I a I. So, in other words, this will be the vector would be sigma 1 a 1 sigma 2 a 2 dot 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 sigma k a k transpose. But what I am saying is that each of these sigma i's is going to look like square root of n by k, each of these ai's is going to look like 1 by square root n. So, this vector itself is going to look like something like square root of n by k times 1 by square root n for every component, which is something like 1 by square root k. It will look like 1 by square root k in every direction. Now, what I do next is, okay, let me add one more page. What I do after this is, I do u sigma v transpose u, right. So, now u is going to be a random rotation, this is going to be a random rotation in Rk. When I say random rotation, it is uniformly at random, right. So, if you have the set of all possible rotations, then I am picking one rotation uniformly at random, which means that after the rotation, the vector, there is no single direction that gets preferred by the vector, right. So, all directions are equally good. That's what it means if I pick a random rotation in Rk, right. So, when I do u sigma v transpose u, then it kind of rotates it, and then it will still leave these values something like 1 by square root k in that order. It won't be exactly 1 by square root k, but then because no direction is preferred, it will be something like 1 by square root k or close to it. So, now if I look at the length, this is my v, right. So, because this was my m. So, if I look at the length squared of v, well, because each term looks like 1 by square root k, the length is going to be 1 by k plus 1 by k plus k times, that is 1, yeah. So, remember we started with u whose length was 1, and then we to avoid any bias in that specific direction u is pointing to, we randomly rotated it in n dimension, so that we got 1 by square root n approximately, and then we took the first k and then made that 1 by square root k by multiplying it approximately by square root n by k, and then we again rotated it in the kth dimension, so that it's still all directions are equally likely. So, 1 by square root k. So, which means that the length is approximately 1. It started with 1, it is still ending up with 1, right. So, basically that's the, if you want to think of m as an operator, so this is why it happens, right. So, no direction has to be preferred, right. So, it has to be truly random. So, and that is the main reason why this whole thing works. Now, it seems so that well, this should happen for any choice of k, right. So, there is nothing, I didn't say anywhere that k has to be small, k has to be this large and so on and so forth, but then J lemma says k has to be at least this much, right. But then this argument did not have anything specific that whatever I discussed so far, though heuristically, I am not saying how big or small k is, but I am kind of making certain heuristic assumptions that this guy has to be a random rotation, the singular values will all look like square root of n by k, this guy will look like random rotation, right. So, now these are, when I say random rotation, I mean uniformly at random, right. So, it is called the Haar measure, but because the rotation matrices are continuous, so you are picking a rotation matrix from what is called as an ensemble of rotation matrices uniformly at random. But this property holds only in high dimension, right. So, this is like an asymptotic property, which means that as d becomes larger and larger when compared to k, Now, these singular vectors of the Gaussian matrix R by square root k look more and more like a random rotation, right. So, they are not random rotations when the singular when let us say d is small, right. So, when compared to k, as d becomes larger and larger, then these look more and more like random rotations. So, only when d is really large, so this is truly a high dimensional phenomenon, right. So, this does not happen in low dimension. Only when d is really large, then these guys truly look like random rotations. In other words, the d by k, right. So, that ratio has to really matters, right. So, if k is also really large, then again we kind of have an issue, right. So, d has to be really large for all this to really work, right. So, for the singular vectors to be truly random, right. Well, if k is large, it will still be okay, but d has to be really large. That is the more important thing. If d is small, then this does not work, right. So, you can do a small experiment, right. So, I am going to suggest all of you to try this experiment. This is a numerical experiment just for you to convince yourself, right. So, let's fix k to be 2 and d to be 3. Okay. Now, what I want you to do is generate M, which is a k cross d matrix, right. So, M is in M belongs to 2 cross 3 matrix, where Mij is standard normal with 0 1 by square root k. In this case, k is 2, so square root 2. Right. So, generate these matrix. So, generate, let us say 1000 such matrices. Okay. Now, what I want you to observe is look at the first singular vector of V, right. So, now do an SVD, break M as U sigma V transpose, and then look at or rather pick first column of V, right. So, of V, right. So, the first singular vector of V and then store it, right. So, let us say call that V1, and now what you have is because you did this experiment 1000 times, you have V1, V2 till V1000. So, what are these? These are one of the singular vectors. So, this is V1 corresponds to the first time I generated the matrix M1. This is M2, another random matrix. This is I generate 1000 random matrices. They have 1000 singular value decompositions, and then I am picking the first singular vector, right. So, I have V1 to V1000. So, all these are in 3 dimension because it is a 2 cross 3 matrix. B would have 3 cross 3. V transpose is 3 cross 3. So, these are all 3 dimensional vectors. Now, fix a random unit vector. Let us call this R in R3. So, in the unit sphere in 3 dimension, right. So, you have the 3 dimensional sphere. Now, pick some vector at random. How can I do this? Well, one way to generate this would be pick something n01, n01, n01. So, this is a 3 dimensional Gaussian vector. Let us call this some W. So, now do W divided by norm W, so that the length becomes 1. So, let us call this R, R equals this. Now, one can show that if you do Gaussian, you generate Gaussian vector and then divide it by its length, what you get is a point uniformly on the unit sphere, right. So, this guy will be uniform on the unit sphere. Now, the experiment that I want to know is to see if V's are uniformly spread around in the unit sphere. Remember, all the V's are orthonormal, right. So, Vi will all be of length 1. They are also somewhere here, right. So, all the 1000 points are here, but I want to know their distribution, right. So, is it like are we preferring one direction over the other, right. So, that is in the unit sphere. Are they uniform? Are the 1000 uniformly spread across the 3 dimensional sphere, or is some direction preferred more than the other. If no direction is preferred more than the other, so then if I take a random vector and then I compute the dot product with the random vector r transpose v1, r transpose v2 till r transpose v1000, right. If I compute the dot product, and now if I do a histogram of these dot products, right. So they should not, prefer one direction, one value more than the other, because r is some random directions. If I have uniformly spread out in all directions, v's are all uniformly spread throughout the sphere, then the dot product with any fixed random vector, should be equally positive, equally negative, right. So it should not be more positive or more negative. But then do this experiment, right. So and then observe this, right. So observe histogram of this. Observe this histogram, right. So and see if you are seeing some bias towards one direction than the other. In other words, does this histogram look uniform, or is it like there is some bias? Of course, it may not be perfectly uniform, but do you see like a lot of bias here? That's the thing that I want you to test. And now once you observe this, then try to increase d to from 3 to, let's say, 1000, right. So or 100 even, right. So 100 or 1000, increase d, right. So now create more high dimensional vectors and then do the same experiment. The experiment is the same, right. So you are still doing SVDs of creating these random Gaussian matrices, creating their singular value decompositions, looking at the spread of the singular vectors, right. So in 1000 dimension you cannot visualize it, and that's why we fix this random vector, take the dot products and then look at these histograms. In 3 dimension you can actually even plot v1 to v1000, but still it might be hard to visually see if they are uniformly spread. But then one measure of checking that would be to fix a random vector and then see the dot products are symmetric about 0. Now if you have done the experiment correctly, what you will observe is when d is small, you will see some bias towards some direction, whereas in d is large, this bias will slowly go away, right. So it will become more and more symmetric. What that means essentially is that the singular vectors become more and more like a random rotation, right. So it is not preferring one direction over the other, though we are looking at the first singular vector for all the 1000 matrices, right. So that is not specifically in pointing to one direction. Some directions are not more important than the others, right. So they are spread out in the unit sphere. You can do it for the second singular vector, third singular vector, does not matter, right. So whichever singular vector it is, right. So they are all going to be uniformly spread around the sphere as d becomes larger and larger. And that means that this whole discussion that we had about v transpose u being removing the bias of u's direction by randomly putting it in some way, so that these are all of the form 1 by square root n, etc., holds true, right. So this numerical experiment might confirm that whatever I am talking about. Of course, we can prove all these things that I am talking about, but then that's going to be much more involved, right. So you'll have to use a lot of random matrix algebra and so on and so forth, which I'm kind of trying to avoid for this course. But this numerical experiment perhaps will give you some insights into what's going on, and why this all that we are talking about does not hold in small dimensions, and we don't want it to hold in small dimensions. I mean, it's not like we don't want to. It's not like we are going to derive use if it holds in small dimensions. The real use of JL lemma comes when d is much larger than k, and all this explanation, intuitively trying to understand this, works in the high dimensional space only. Okay, so that's the linear algebraic explanation of JL lemma. So with this, we have completed one of the main ideas of dealing with scale in machine learning using random projections, which is the Johnson-Lindenstrauss Lemma. Of course, we will see some applications of this directly or indirectly as we go along and talk about other topics in the future lectures of this course. But as such, this is a very powerful tool that can be used for dimensionality reduction in machine learning for any downstream task, be it nearest neighbors, be it there are your support vector machines, whatever you want to do, you can apply JL lemma and then perhaps work with an algorithm that only makes use of pairwise distances. So it's a powerful lemma, and then that's where we will we have started our discussion about algorithms for data science at scale, and then we'll start looking at other algorithms in the future lectures. Thank you.